Hi, this is Mrs. Basin. In this screencast, we're going to talk about naming ionic compounds with polyatomic ions. So when we have a polyatomic ion, what this is a charged entity that has a group of nonmetals that are bound together with covalent bonds. But as a group, they're bound together, but they have a charge overall, so they then behave as an ion when they combine with another ion to form an ionic bond. They are assigned special names, so they're not names from the periodic table. Each of these groups of atoms has their own name. So the easiest way to do this is to memorize those names of those polyatomic ions, and then it's a lot easier to recognize them when you're going through and naming compounds. Here's a list of some of the more common ones, and I'll give you another list in class, but you can see how it's groups of atoms, and the charges can be anywhere from +1 to -1, all the way up to -3. Notice there is only one positive polyatomic ion, the rest of them are all negative. And there are also a couple that have multiple names. So like this one here, it could be called hydrogen sulfate, but it's also called bisulfate. This one over here is hydrogen carbonate, but it's also called bicarbonate, like sodium bicarbonate, which is baking soda. So again, there's some that could have multiple names. The other term that we're going to look at is something called an oxyanion. These are polyatomic ions that have an element and different numbers of oxygen atoms. And a lot of times there'll be several of these in a series where their oxygen atoms are bound to the same element, but in one case there might be 2, and the next case there might be 3. So when these are named, when the polyatomic ions are named, the one with the smaller number of oxygen atoms ends in ITE, and the one with the larger number ends in ATE. So the ITE and the ATE are not assigned specific numerical values, but when you have a series, the ite is always the lower number of oxygens, and the ate is always the higher number of oxygens. So for example, SO3 minus SO4, the SO3 is sulfite, so SO3 minus 2 is sulfite, and then SO4 minus 2 is sulfate. When you have more than 2 oxyanions, you can also add on the prefix hypo and per to name the numbers in a series that have the fewest and the most. So if you have a series that has 2 and 3 as your ite and ate, if it has 1, it would be hypo-ite, and if it has 4, it would be per-ate. So here's an example. So I'm going to put all these on here so you can see here. Here's chlorite and then chlorate. So chlorite has 2 oxygens, chlorate has 3. One less than the ite is hypo-ite, so 1 oxygen would be hypochlorite, and then 1 more than 8 is perchlorate. So ClO4 would be perchlorate. So the ite and the ate still are the lower number goes to the ite, the larger number goes to the ate, but if you go 1 less than ite, it's hypoite, 1 more than 8 is per-ate. Okay, so when we go to actually name these, the first part of the compound is named using the element name with a Roman numeral if necessary. So again, we're still worried about whether it's a single charged metal or a multiple charged metal. If it's a multiple charged metal, you still use the Roman numeral. Or the first part of the name could be that positive polyatomic ion that we talked about. And again, there's only one of those, ammonium, NH4+. So these names will either start with the name of the metal or the name of that positive polyatomic ion. And then the second part of the compound is named using the name of whatever polyatomic ion is present. So just like always, the easiest way to do these is to do some examples. So let's look through these. So here's our first example, Na2SO4. So the first part of that would be named sodium. And sodium is a single charged metal, so we don't need to worry about a a Roman numeral. And then the second piece of this is the polyatomic ion sulfate. Okay, and this kind of shows you why it would be helpful to have those memorized. If you don't have them memorized, then you would want to have your list out that I'll give you in class. So this would be called sodium sulfate. As you're looking at these, the way you will be able to tell the difference between these and the other ones that we've talked about so far is that these are not binary compounds. So up to this point, we've looked at only naming compounds that have 2 elements in them. These elements, or these compounds, if you notice, all have more than 2 elements present. So you'll know that one of those pieces at least is a polyatomic ion. Okay, so we look at our second example. The first piece of this is iron. And iron, if you remember from talking about this in class the last few days, iron is a multiple charge metal. So to figure out what the charge is on iron, we have to think about what is the charge of nitrate. So nitrate is a -1 as a group, so this whole thing has a -1. So if there are 3 of those present, that has an overall charge of -3, so that means iron would have to be a +3 for that whole thing to balance out to 0. So this would be iron 3, and again, we have to show that in Roman numeral because iron can have multiple charges. Iron is on our list of multiple charge metals. And then the second part of this, NO3, is the name of that polyatomic ion. So in this case, this is nitrate. And again, going off the list if you don't have those memorized. So the second one again would be iron 3 nitrate. My third example, Na2SO4. Sodium, again, is the first part of this. I don't need a Roman numeral because this is not a multiple charge metal. And then my second part is the polyatomic ion, and this time we have SO3 instead of SO4 like we had in the beginning. So this one is sodium sulfite. Then my last example, K3PO4. I start this with potassium. I don't need a Roman numeral because potassium is not multiple charge. And then the name of my polyatomic, which is the second part of this, and that would be phosphate. Okay, and I'm going to add one example up here at the top because we did not see an example of one that has the, I'm going to try to put this at the bottom here, one that has the positive polyatomic ion. So if we look at this one, let's say this is NH4Cl. So this case, this is the polyatomic, the NH4, the first part. So this one would be called ammonium. And then the second part of that, we'd name it like we always have. This would just be chloride. So that would be ammonium chloride. The other thing you could see is you could have 2 polyatomic ions. So I could have NH4, let's say NH4OH. Okay, so this is a polyatomic ion, and this is a polyatomic ion. And again, the only time you'll see this is when it starts with NH4, because NH4, like we said, was our only positive polyatomic. So the name of this compound would just be the name of the 2 polyatomics. So this would be ammonium, which is the name of this, and then the name in the second part would be the name of my OH, which is hydroxide. So again, NH4OH would be called ammonium hydroxide. Okay, so my last part of this is looking at writing formulas for the ionic compounds that have polyatomic ions, and the format is going to be similar to what we've done so far. So again, we'll look at some example problems here. So my first one, copper 2 nitrate. So this one, I'm going to start with copper, which is a +2, and I know that, even though copper is multiple charge, I know it's +2 because that Roman numeral belongs to the metal. So copper 2, and then nitrate is NO3 minus. Again, that's either memorized or that comes from the list of all the polyatomics that we have. So copper nitrate would then become, when these crisscross down, CuNO3 parentheses 2. The reason I have to put the parentheses there is because when this 2 comes down, it goes to this whole thing. So I have to put the parentheses there to show that that 2 gets distributed to that whole polyatomic ion. So this essentially means this is copper with 2 groups of these nitrate polyatomics attached to it. Next example, lead carbonate. So lead is Pb. The charge on lead is +2, and I know that because of my Roman numeral. And then carbonate is my polyatomic here, so that is CO3 minus 2. So this becomes Pb2, CO3 2, which those are going to cancel each other out, so it just becomes PbCO3. Next example, potassium sulfite. Potassium is K. Potassium is a single charge metal, so it's always a +1. And then sulfite is SO3 minus 2. Again, that comes off my list of polyatomics, or you have it memorized. Crisscross charges here, so this becomes K2SO3. And then my last example, ammonium chlorate. This is another example of two polyatomics bonded together. So ammonium, again, is our only positive polyatomic. So it's NH4+. And then chlorate is ClO3-. So when those crisscross, I end up with NH4ClO3. So that's my formula for ammonium chloride. So same method, or I'm sorry, ammonium chlorate. Same method as before. You are looking at the charges, crisscrossing, and then putting them in their lowest form by either reducing them or canceling out ones that are similar.